welcome to Unit 1, Lesson 5, Limits at Infinity. So today we're going to be looking at determining limits that go to either positive or negative infinity, and we're going to be trying to connect limits at infinity with some things that we already know about vertical and horizontal asymptotes. So in the previous lesson, you saw that you could remove a discontinuity by ensuring that the limit from the left and the limit from the right were equal. Well, that's not always going to be the case. Some discontinuities are just not removable, and those exist at vertical asymptotes. And in this lesson, we're also going to be looking at trying to make connections between something you already know about horizontal asymptotes and limits at infinity. So just a quick reminder about the definition of a vertical asymptote. Now that we know some things about limits, we can apply that idea. So we say that if a function f of x approaches infinity or negative infinity, as x approaches some number c from the right or the left, then the line x is equal to c is considered to be a vertical asymptote of the graph of f. If the graph of a function has a vertical asymptote at x is equal to c, then we say that f is not continuous at c. This type of discontinuity is called infinite or asymptotic discontinuity, and it's not removable. So you can see in the graph there's an example that is the limit of the function 1 over quantity x minus 1 squared as x approaches 1, we could say is equal to infinity, or sometimes we might say it approaches infinity. But ultimately, something to remember is that on an AP exam, a limit that approaches infinity, either positive or negative, is said to not exist. And those two answers of infinity, and not existing are interchangeable. So a quick list of some properties of infinite limits. So say we have two functions f and g, and the limit of f as x approaches c is infinity, and the limit of g as x approaches c is L, some real number. Then if I were to want to know what the limit of the sum of those functions are, well, the infinity sort of supersedes whatever the limit of g is approaching. So the total limit there is infinity. The same thing sort of happens with products, but we have to consider the fact that if L is positive, then I'll end up going to positive infinity. And if L is negative, I'll end up going to negative infinity. Now with the quotient rule, if the denominator of a rational function approaches infinity, you can think about this as dividing by some number that's getting larger and larger and larger and larger. And in that case, the limit is always going to be 0. So, quick example. We want to find the limit of this function 5 minus 2 over x squared. So, the limit as x approaches infinity of 5 minus 2 over x squared, let's apply some of our limit rules or limit properties. We can break this up into two separate limits and find the difference of the limits. Now the limit as x approaches infinity of 5, that's just a constant. 5 is always 5, regardless of the value of x. So the limit as x approaches infinity is 5. The function 2 over x squared is a rational function. The denominator has the largest degree. So the limit as x approaches infinity should approach whatever horizontal asymptote that rational function has. And in this case, that's y is equal to 0. Simplifying, we get an answer of 5 for this limit. So again, just an explanation about the rational function part. The function 2 over x squared has a horizontal asymptote at y equals 0. So as x goes to infinity, that part of the function approaches 0. If you need a refresher on how to determine horizontal asymptotes, I've linked a quick YouTube video. It's about 10 minutes long, and you can check that out to get a refresher about how to determine horizontal asymptotes for rational functions. It's a really important skill that you're going to use a lot in this class. Hey, example number 2, we want to find the limit as x approaches negative infinity, the square root of x squared plus 3 over 2x minus 9. Now, I love this problem because it involves your understanding of horizontal asymptotes and a little bit of fudging the numbers, which happens quite often sometimes in this class. So consider the fact that at infinity or even negative infinity, the value of plus 3 and minus 9 has very little impact. It becomes rather insignificant, as x is the value that's growing to infinity. So we can sort of think of this function as really just x squared, the square root of x squared over 2x. Now simplifying this, the square root of x squared is a definition for the absolute value of x. So really what we want to think about is the rational function, the absolute value of x over 2x. Now this has a horizontal asymptote of plus and minus 1/2. Again, the reason for that, you can review finding horizontal asymptotes in the video linked in the previous slide. But quickly, this rational function has a degree of 1 in the numerator and a degree of 1 in the denominator. And because the degrees are the same, we're looking at the ratio of coefficients. However, because the numerator is always positive due to the absolute value, and the denominator could be negative when x is less than 0, the horizontal asymptote is not just 1/2. It's 1/2 when x is greater than 0, and negative 1/2 when x is less than 0. So because x is approaching negative infinity, we say that the limit that we are trying to find is negative 1/2. So in review, when determining limits at infinity, it's helpful to consider the function if the function has any horizontal asymptotes. If it does, then the horizontal asymptote is the limit at infinity. Any limit that approaches infinity, both positive and negative, should be considered to not exist, especially on your AP exam.